Students, now the completion of Werner theory and its applications. Now we are coming to our next concept, EAN rule. EAN rule, dear students, proposed by a scientist under name Sigmund. Dear students, what is EAN, sir? EAN simply defined as effective atomic number. If you want to know about its definition, EAN is simply the total number of electrons surrounded by a central metal atom or ion in a given complex. Dear students, according to Sigmund, if EAN of a given complex is equals to a inert gas atomic number, then absolutely the complex said to be more stable. So this is what we call simply EAN. Then while we coming to the definition, EAN is simply the total number of electrons surrounded by a central metal atom or ion, whatever it may be, in a given complex. Sir, how one can find EAN for a given complex, sir? Calculate. We have formula to calculate EAN. Dear students, just look at that. Atomic number of central metal atom or ion minus its oxidation state plus the total number of electrons gained by central metal ion from ligands. Dear students, and this is the formula to calculate EAN. Once again I repeat it. Atomic number of central metal atom or ion minus its oxidation state plus the total number of electrons gained by central metal ion from ligands. To calculate EAN, we are ready to choose our first complex K4 FeCN6. Now we are ready to calculate its EAN. When we look at the formula, what is going on? Atomic number of central metal atom or ion. What is central metal atom or ion in this particular complex? I think iron. Say sir, no. What is atomic number? Iron atomic number 26 minus, my dear students, now we are ready to write its oxidation state in that particular complex. Okay, and you guess what is the oxidation state of iron in that particular complex? +2, absolutely. If you have any doubt, we are ready to calculate oxidation state at one corner. FeCN6 being this is K4, I think this is -4. Say this is X, for which oxidation state to be calculated, and cyanide being a negative ligand, -1. And this is, I think, X minus 6 is equal to -4, absolutely X is +2. And that's why minus oxidation state means -2. Plus total number of electrons gained by central metal ion from ligands. We know all the bonds present in complex is absolutely dead bonds. So each ligand ready to donate how many electrons? 2 electrons. How many ligands are there? So each ligand donates 2 electrons, means the total number of electrons gained by central metal ion from ligands is absolutely 12. Is it fair? Now let me come into EAN. What value finally we have? I think this is 26 minus 2 plus 12 and absolutely I think 36. Am I right or not? Are you guess 36 is the atomic number of which element? Come on, we know noble gases very well. Okay, helium, neon, argon, krypton, xenon, like that. Hey, come on, helium, neon, argon, krypton, xenon, is not it? What is the atomic number of helium? 2. What about neon? After adding 8, kada. What about argon? After adding 8 once again. What about krypton? 36. Because now we are ready to add 18. Because we know regular intervals and classification of elements have 2, 8, 8, 18, 18, 36. Then 36 if you got EAN, which is actually the atomic number of krypton, which is a noble gas, inert gas, yes or no? So according to Sedgwick, if EAN of a given complex is equals to inert gas atomic number, and absolutely that complex appears to be more stable. Is it fair, students? So that's why here 36 is atomic number of an inert gas what we call krypton, and that's why K4FeCN6 appears to be, dear students, more stable. Keep in mind, this is the way how one can calculate EAN for a given complex. Then it's very clear, students, what is EAN? Effective atomic number. Students, are you ready to calculate effective atomic number for tetracarbonyl nickel, please? Tetracarbonyl nickel. How are you ready to calculate EAN for this complex? Dear students, what about atomic number of nickel? Come on, 28. And you guess its oxidation state? 0. Why it is 0, man? Say nickel some X. What about carbonyl? I think there is a neutral complex. Carbon monoxide is a neutral complex. We are ready to write here this is 0, man. Okay. X plus 4 into 0 is equal to 0. So what about oxidation state means X plus 4 into 0 is equal to 0. Then absolutely X is equal to 0. Oxidation state 0. Total number of electrons gained by central metal atom or ion, whatever it may be. 4 ligands are there, students. 4 into 2, 8 electrons, and that's why 28 plus 8, dear students, what it is? 36. Once again, we got inert gas configuration, which confirms that tetracarbonyl nickel is also, come on students, a stable complex. Please. Now I'm ready to give you examples to calculate EAN. CO NH3 6 plus 3 K2 PG Cl6. Dear friends, next one K3 Fe CN6. Could you please calculate the EANs for these three complexes? Apply the same formula, students. Apply the same formula. And also we are ready to write here the other one, NiCN4 minus 2. Students, what about the first one? Cobalt NH36 plus 3. If you want to write effective atomic number, first of all we have to write its atomic number 27. Students are agree with me? What about its oxidation state, man? Plus 3 its oxidation state. Yes or no? Just imagine, say here is some X, ammonia being a neutral compound, 0. So X plus 6 into 0 is equal to 3 plus 3. Then absolutely X is 3. Means oxidation state 3. 6 ligands are there, each donate 2 electrons. Is it fair? So I think 36 once again, students, yes or no? 36 once again. 24 plus 12, absolutely. So that complex also appears to be more stable, yes or no? Students, what we coming to the second one? K2, Pt, Cl6. And here a confusion arises. What is the atomic number of platinums or like that? Okay. How one can know about the atomic number of such a heavier elements? What is osmium, iridium, platinum? Yes, these absolutely belongs to 5D series of elements. And remember transition triodes. Come on. In 3D series, iron, cobalt, nickel. In 4D series, ruthenium, rhodium, palladium. And in 6D series, 5D series, osmium, iridium, platinum. Okay. Students, come on. This is iron, cobalt, nickel. And this is ruthenium, rhodium, palladium. And this is osmium, iridium, platinum. Sir, I know nickel atomic number 28. What about palladium, man? We just add 18, that's enough. Okay, because while we coming to 3D to 4D, addition of 18 electrons enough. Means what it is? Palladium after adding 18, I think 46, yes or no? Sir, what about from 4D to 5D? 4D to 5D means which period? 6th period, no confusion. 5D series means which period? 6th period. Is in 6th period, Lanthanides are there? Say sir, no. Lanthanides are there in 6th period or not? Absolutely. Lanthanides are located in 6th period, man. After lanthanum, from cerium to lutetium. Say sir, no. So that's why now we are not ready to add 18 here. We are ready to add 32. Keep in mind. Okay, we just add 32, man. What it is? 70. This is the atomic number of platinum. And that is the way how you can know the atomic number of even D block elements also. Okay, sir, what about osmium, sir? What about osmium? Okay, now, what about osmium? Stupid question, sir. 77, 76, not like that. Okay, now. So, iron nunchi calculate cheyalli. Iron being 26, we add just 18 to get ruthenium first. Okay, now 26 plus 8, 44. Am I right? What about osmium, sir? 44 plus 32. Is it bad? What is, sir? 76. This is the way how one can find the atomic number of each and every D block element. Either they belongs to 3D series, or they belongs to 4D series, or they belongs to 5D series, whatever it may be. Okay, so after knowing the atomic number of platinum, it becomes easy. What about atomic number of platinum, sir? 78. About its oxidation state, man. What about its oxidation state? I think that is plus 4. Okay, if you have any doubt, you just calculate that. Say this is platinum, Cl6 being K2. I think this is minus 1. Am I right, friends? This is X, this is minus 1. Okay, then I think X minus 6 is equal to minus 2. X is absolutely plus 4. Then we have to write 4 here. How many ligands are there? 6 ligands. So each donate 2 electrons. Then absolutely 74 plus 12, 86. And here the thing is, sir, 86 is a unit gas configuration atomic number, sir. Okay, let us see. Okay, helium, neon, argon, krypton, xenon, radon, etc. What about helium? Atomic number 2. What about neon? What about argon? What about krypton? Yes, 36. What about xenon? Come on, we add them again 18. What it is? 36 plus 18. 50. 54. What about right answer? We are ready to add 32 now. 54 plus 32. That's 86 here. That's 86 here. Okay, then 86 means what atomic number, sir? 86 means radon atomic number, dear students, and that's why these two complexes appears to be very more stable. Okay, now because their atomic number is absolutely equals to inert gas atomic number. Their EAN is equal to inert gas atomic number. What about the last two? K3 FeCN6. Students, 26. Am I right? If you are ready to calculate its oxidation state, I think this is 3. Are you agree with me or not? Are you agree with me or not, man? This is minus 3, I think it is. Say this is x. X minus 6 is equal to minus 3. Then what about x man? Plus 3. Say yes or no? Thank you. What about number of electrons donated by ligands? 6 into 2. Then what about its effective atomic number? 30. According to Sidgwick, this is unstable. Okay, but while we come to reality, when we look at K4 FeCN6, iron exists in what oxidation state? Plus 2. While we come to K3 FeCN6, iron exists in what oxidation state? Plus 3. Just check in your mind. With respect to iron, plus 3 is more stable than plus 2. Why, sir? Why? Because plus 2 means 3d6. Plus 3 means 3d5. 3d5 appears to be more stable due to half-filled configuration. But according to Sidgwick, this is unstable. Okay, now this is not at all fair. So once we come into reality, this is also a more stable complex, and that's why Sidgwick theory, which is the complex having effective atomic number equals to inert gas atomic number are only stable, is somewhat not at all possible. Okay, Nanda. So the calculation of EAN is of course very important for our examination point of view. But the thing what happens according to Sidgwick, only those complexes in which EAN is exactly equals to inert gas atomic number are only stable complexes is not at all possible. Okay, now because there are some complexes which appears to be more stable, but however their effective atomic number is not equals to inert gas atomic number. Is that got it? Okay, now what about this one? What about this one? NiCN4 minus 2. What about this one? 28. Am I right, students? I think 2 oxidation state. Say sir. Thank you. This is 2. What about number of electrons donated by ligands? I think 4 into 2. Am I right, students? Okay. I think this is 34. If I am right. If I am right, that is 34. Say sir, no? 34 is not at all the inert gas configured atomic number. But still, NiCN4 minus appears to be what man? More. Very important one. Okay, now. But students, in entrance examination point of view, there are some difficult questions here. Just look at that. MnCO5. Could you please calculate effective atomic number for what is atomic number? What is IUPAC name first of all? MnCO5. What is IUPAC name? MnCO5. IUPAC name. Penta, carbonyl, manganate, manganese. Manganese. Negative state కాదు కదా బ్రాకెట్ లో ఆక్సిడేషన్ స్టేట్ ఎంత బ్రాకెట్ లో ఆక్సిడేషన్ స్టేట్ 0 ఆక్సిడేషన్ స్టేట్ ఏం లేదు కదా దాన్ని కట్ ఒకసారి ఎఫెక్టివ్ atomic number కట్ ఎంత వచ్చింది 35 అయితే కరెక్ట్ పిల్లలు నేను చేస్తా లేకపోతే మీకు రాకపోతే ఒకసారి మాంగనీస్ అంటే మా అటామిక్ నెంబర్ అంతేనా ఆక్సిడేషన్ స్టేట్ ఎంత థ్యాంక్ యూ లైగెండ్స్ 5 నాన్న 5 into 2 10 కదా సో ఎఫెక్టివ్ అటామిక్ నెంబర్ ఎంత నాన్న 35 it is not a energetic atomic number is it fair but the thing is sir why MnCO5 exists to be dimer because MnCO5 exists as a dimer as Mn2 dear students CO10 okay now so this is how MnCO5 upon dimerization it exists as a dimer because once it exists as a dimer this MnCO5 gain one more electron చేశారు డైమరైజేషన్ జరుగుతుందంటే ఒక ఎలక్ట్రాన్ ఏం చేస్తుంది ఖచ్చితంగా గెయిన్ చేస్తుంది సో వన్స్ ఇట్ గెయిన్ వన్ మోర్ ఎలక్ట్రాన్ 35 electrons becomes 36 in such a manner MnCO5 appears to be more stable dear students in its dimerization form than compared to MnCO5 because MnCO5 follows Sedgwick EAN rule not in monoform but in which form nana dimer form is it clear students okay so why MnCO5 exists as a dimer sir it exists as a dimer to satisfy Sedgwick EAN rule to get a inert gas atomic number which appears to be more stable please so Mn2 CO10 అందువల్ల మనకి డైమర్ కింద ఎగ్జిస్ట్ next nana vanadium CO6 vanadium CO6 ఇవంతా చూడండి vanadium CO6 పిల్లలు 23 అమ్మా vanadium ఏనా ఆక్సిజన్ స్టేట్ 1 సెకండ్ 0 రా -0 కదా ఏనా ప్లస్ 12 అమ్మా చూడండి ఇది కూడా ఎంత రానన్నా 35 ఎలక్ట్రాన్స్ ఏదా ఇప్పుడు ఇది కూడా ఒక ఎలక్ట్రాన్ గెయిన్ చేసింది అనుకోనన్నా ఏ కాన్ఫిగరేషన్ వస్తుందిరా వాటికి ఇనర్ట్ గ్యాస్ కాన్ఫిగరేషన్ if VCO6 gain one electron like VCO6 -1 then absolutely the EAN becomes how many electrons ranana 36 electrons and it appears to be very stable and here MnCO5 also gain one electron then students these complexes plays what role in chemical reactions according to you and my intention is their act as oxidizing agents or reducing agents like that okay na so how one can confirm sir they act as oxidizing agents or reducing agents before knowing they act as oxidizing agents or reducing agents first of all we look at that what's their dimension so oxidize or reduce okay na so these two complexes are ready to gain electron okay na gain electron is a phenomena of reduction say sir okay so means they are reduced themselves వాటంతటా అవి రెడ్యూస్ అవుతున్నాయంటే what is their role they act as oxidizing agents simple logic so that's why these two complexes acts as a strong oxidizing agent sir what is the reason behind that sir the reason behind that is to get stability by satisfying Sedgwick EAN guys have you got it please make it ఇవన్నీ కూడా మనం కాస్త డెప్త్కి వెళ్ళినప్పుడు వాడు ఆబ్జెక్టివ్ పాయింట్ ఆఫ్ వ్యూలో మనల్ని క్వశ్చన్ చేస్తాడు ఎందుకంటే తర్వాత మెటల్ కార్బోనైల్స్ దగ్గర ఎలాగో మాట్లాడాలి ఇవన్నీ మనం మీకు బిట్స్ ఇప్పుడే కనబడతాయి మన మెటల్ కార్బోనైల్స్కి వెళ్ళే ముందే ఇలాంటి బిట్స్ కనబడతాయి అందువల్ల మనం దీన్ని కూడా MnCO4 కిందే రాయొచ్చు CO5 minus. Next, VCO5, here students, minus 3, CrCO5 minus 2, and MnCO5 minus. These three are, dear students, isoelectronic and isostructural with which of the following complex? What an objective question. ఆ మూడు కాంప్లెక్సెస్ కూడా క్రింది వాటిలో ఏ కాంప్లెక్స్ తో ఐసోఎలక్ట్రానిక్ మరియు ఐసోస్ట్రక్చరల్ గా ఉంటాయి? వెరీ వెరీ ఇంట్రెస్టింగ్ వన్. ఇప్పుడు వీటన్నిటికీ EAN ఎంత? ఆ పైన ఉన్న చార్ట్తో సహా చెప్పాలి, సరేనా? నువ్వు నేరుగా కట్టేస్తే ఇది 35 ఆర్ నాట్ 35, 23 ప్లస్ 10 33 కదమ్మా. మైనస్ 3 అంటే 33 ప్లస్ 3 అంటే 3 ఎలక్ట్రాన్ తీసుకుంటారమ్మా, అవునా? ఎంత ఎంత చెక్ పెట్టాము. వాట్ అబౌట్ నెక్స్ట్ వన్? 24 plus 10 actually plus 36. Next one 35 plus 1 36. They are all isostructure and isoelectronic with FeCO5. Just look at that. That's enough. Because FeCO5 means 26 plus 10 36 absolutely isoelectronic. ఎందుకంటే 4 స్పీషీస్ లో మనకు ఉన్నవి సేమ్ నెంబర్ ఆఫ్ ఎలక్ట్రాన్స్. అరే ఉన్నవి 5 కదా లైగెండ్స్. సో దే ఆర్ ఆల్ హ్యావింగ్ సచ్ ఏ షేప్ వాట్ వి కాల్ ట్రయోగోనల్ బైథర్మల్. ఐసోస్ట్రక్చరల్ అండ్ ఐసో ఎలక్ట్రానిక్. కీప్ ఇన్ మైండ్. ఓకేనా? అండ్ నౌ లెట్ మీ ఇంట్రడ్యూస్ another one. Titanium CO6 minus 2 and vanadium CO6 minus 1, isoelectronic and isostructural with a metal M CO6. What is metal M here? What an important objective question. What is metal M here? Okay, now come on, guess what is metal M here, students? M may be scandium or titanium once again, or vanadium or chromium or manganese, whatever it may be. Okay, while we coming to effective atomic number for this species, titanium being 22, 22 plus 12, 34, along with minus 2, 36 absolutely. What about vanadium CO6 minus 1, sir? I think 36. Okay, and here I am having only what we call 12 electrons donated from ligands. If it is also having EAN 36 minus 12, 24. Okay na? అంటే అక్కడ ఉన్నటువంటి మెటల్ M అటామిక్ నెంబర్ ఎంత అవ్వాలిరా? 24 అవ్వాలి. ఇది 24 అయితేనే కదమ్మా అప్పుడు దానికి కూడా ఎఫెక్టివ్ అటామిక్ నెంబర్ ఎంత అవుతుందిరా? 36 అవుతుంది. So if M is equal to 24, means my intention is atomic number is 24, then these three species are isoelectronic and isostructural. Okay na? Then what is M here, students? What is M here? Come on. Chromium. This is an objective, sir. Okay na? When we know about Situate EAN rule, doubt na. So you can know objective point of view EAN rule మీద మనం కాస్త క్లారిటీని పెట్టుకుందాం. ఓకేనా? So this is EAN rule and some conditions. And students, in tomorrow class we will entering into a great theory what we call valency bond theory, because we have some drawbacks in our previous Werner theory. I remember drawbacks. The first major drawback is there is no correlation exist between electronic configuration of central metal ion versus the number of electrons taken by length. Okay, now, and also Werner theory doesn't explain about color of complex. Werner theory doesn't explain about magnetic behavior. Okay, so we will explain all the drawbacks what we found in Werner theory. We choose another greatest theory what we have, valency bond theory. And tomorrow class, I am ready to explain valency bond theory. Dear students, please make a note, and all these are very important towards EAN.